Welcome to Chapter 2.3, Understanding and Interpreting Standard Deviation. Now, in this section, we go beyond calculation. You already know how to find a standard deviation. We covered that last time. Now we're going to talk about how to use it. This includes tools that let us describe where most values lie in a data set and how confident we can be in those estimates. We'll focus on two powerful ideas, Chebyshev's theorem and the empirical rule. So why do we care about how values are spread around the mean? Because two data sets can have the same average but behave very differently. Imagine two delivery services, both promise 30-minute delivery on average. One's very consistent, almost always arriving within 28 to 32 minutes. The other varies wildly, sometimes 10 minutes early, sometimes 45 minutes late. Even though the mean is the same, the variability, and thus your experience, is very different. That's why we need rules to interpret standard deviation in context. The first tool we'll look at is Chebyshev's theorem. This is incredibly useful because it works for any distribution, skewed, uniform, bell-shaped, you name it. The rule says for any k greater than or equal to 1, at least 1 minus 1 over k squared of the data values fall within the mean plus or minus k standard deviations. We're going to get to an example in a second that makes that make sense, all right? But what that means is that no matter what the data looks like, a certain minimum percentage of values will be within 2, 3, or more standard deviations of the mean. It's not exact, it's a lower bound. But that's what makes it conservative and reliable. It really is saying at least, the emphasis on the at least there. Often it'll be more. The table on the page at the bottom here shows some common values for Chebyshev's theorem. For k equals 2, at least 75% of the values fall within 2 standard deviations of the mean. For k equals 3, at least 88.9% of the values fall within 3 standard deviations. There's no guarantee that the data looks symmetric or normal, just that most of it is somewhere near the mean. This is extremely helpful when you're working with real-world data that's messy or not bell-shaped. All right, let's look at an example. So here, a data set has a mean of 75 and a standard deviation of 100. Now, notice if the standard deviation is 100, then to get to the variance, it would be the square root of that value. The square root of 100 is 10. So, if I'm going to calculate the mean plus or minus 2 standard deviations, that would translate to 75 plus or minus 2 times 10, or 75 plus or minus 20. Well, minusing the 20, right, subtracting 20 gives me 55. And adding 20 gives me 95, 75 plus 20. So the interval from 55 to 95 would contain 75% of the data in that interval, at minimum, right? That's the lower estimate of Chebyshev's rule. We're going right off of what's right here. Now, by the way, where's that 75% coming from? It's from this formula right here, right? We're plugging in k equals 2. So we're going, right, why is it 2? That's the value right there, right? matching up. So plugging in 2 here, we'd have 1 minus 1 over 2 squared, or 1 minus 1/4. 1 minus 1/4 is 3/4, or 0.75, so 75%. All right, so 75% we're guaranteed of our data it will find between the interval 55 to 95. Let's do the mean plus or minus 3 standard deviations. So now that's the mean, which is 75, plus or minus 3 times 10. So that's 75 plus or minus 30. Okay, again, subtracting 75 minus 30, because we always do the smaller one first. That takes me to 45. Now 75 plus 30 would take me to 105. So the interval from 45 to 105, we know that at least 88.9% of the data lies in that interval. Again, I'm coming right off of here, right? We already figured it out for 3, again, using this formula right up here. All right, so we don't have to know the shape of the data. These intervals give us guaranteed minimum coverage. That is a powerful tool. Now let's look at the empirical, which is also known as the 65, 95, 99.7 rule. This one is faster and more specific, but it only applies to bell-shaped curves or normal distributions. Here's how it works. About 68% of the data fall within 1 standard deviation of the mean. Go up or down by 1 standard deviation, add or subtract 1 standard deviation to the mean, and about 68% of the data will fall in that interval. 95% falls within 2 standard deviations, and 99.7% within 3 standard deviations. This rule helps you make quick mental estimates about where data will fall when the distribution is approximately normal, when it's bell-shaped. Okay, here's an example. Suppose the time to complete a manufacturing task is normally distributed with a mean of 12.8 and a standard deviation of 1.7. All right, what does that mean? Normally distributed means we've got that bell-shaped curve. The peak is where the mean is. And that mean we said was 12.8. So right at the height, right? This is my number line. Right at the height of the peak, that should be where the mean is. Okay, 1 standard deviation down and up, we're going to take mu plus or minus 1 sigma, 1 standard deviation. So that's 12.8 plus or minus 1.7. So if I do 12.8 minus 1.7 first, that's going to take me to 11.1. And then if I take 12.8 plus 1.7, that's going to take me to 14.5. Now, because of the symmetry, the 14.5 should lie about the same distance from 12.8 as I put the 11.1. So this interval is 1 standard deviation up and down. Our empirical rule says we'll find 68% of the data lying in that interval, lying in that interval 11.1 to 14.5. Okay. Now we're going to subtract 1.7 again. Now notice I could do 2 times 1.7 and subtract it from 12.8, but I can just also subtract 1.7 again from the 11.1. Okay, so that will take me down to what? 9.5. Did I do that right? No, I didn't. 9.5 would be 11.2. So it would be 9.4. Whoops. Okay, so 9.4 going this way. I'm just subtracting 1.7. Add 1.7, and that's 16.2. All right, so now in this interval, let's change colors here so we can see it a little bit better. In this interval, from here to here, this contains 95% of our data. All right, so 95% of the data lies in the interval from 9.4 to 16.2. Okay, let's change colors once again. How about green? Okay. So now our last one is 3 standard deviations out. So we're going to subtract 1.7 again. So that's 8.4, 7.7, 7.7. And then add 1.7 again. So that takes me to 17.9. So now from here to here, all of that data is the 99.7%, right? So 99.7% of my data lies in that interval from 7.7 to 17.9. That's a 17.9. Okay. So that tells us the company that nearly all the jobs would be completed within about 7.7 to 17.9 minutes. That's pretty useful for planning. Okay, so how do Chebyshev's and the empirical rule compare? Well, Chebyshev's is universal. It works on any data set, no matter what the shape is, but it gives conservative results. The empirical rule is more precise, but only valid for bell-shaped curves. So use Chebyshev's when you don't know the shape or have odd data. Use the empirical rule when the data is symmetric and looks like a normal curve. All right, let's wrap this up with some key takeaways from this section. So the standard deviation helps us understand how spread out the data is from the mean. Chebyshev's theorem provides a conservative estimate of spread for any data set, regardless of the shape. The empirical rule offers faster, more specific guidance, but only for mound shape or normal distributions. Most values fall within 1 to 3 standard deviations of the mean. That's true in theory and often in practice. These tools help us make informed predictions and understand how typical or unusual a value really is. The more you use these interpretations, the more intuitive they become. They're useful tools for quality control, risk analysis, and decision-making in business, science, and beyond. Standard deviation is powerful, not just as a formula, but as a way of predicting how data behaves. Whether you use Chebyshev's theorem for messy data or the empirical rule for bell-shaped data, these tools give you meaningful expectations about how far data values typically fall from the mean.